Welcome to my session here at JCon 2021. I will just jump in and start sharing my screen real quick. All right, so give me a second. All right, I hope everybody can see my slide deck here. And with that, again, welcome to my talk. Thanks very much for taking the time to join. This talk will be given in English, as it is in the as it says in the schedule. However, I'm German, as probably most of the speakers here in a German conference. However, what I would like to do, I would like to have this session as interactive as possible. So if you have any questions throughout the talk, you can either use the chat, but I would prefer just feel free to unmute your phone and ask me things directly. I'm not sure if I will be able to monitor the chat all the time. Also, if you have any issues asking your questions in English, you can of course feel free to ask the question in German, and I'm going to translate them for English and German speakers then. So I just want to make sure you take all the things out of that talk that is possible. Now, a few words to myself. That was a photo of me prior to the lockdown times when I still had a short and decent haircut. Things have changed a little bit in the meantime. I'm working for a company called Novatech here in the southern part of Germany, and are mostly busy with helping clients migrate their organization or their workloads to a modernized stack, most likely the cloud. And this is also part of the things I'm going to talk today. So I've got a Twitter handle. I'm actually pretty active there. So if you have any questions, feel free to ping me there. Also, the things I'm going to do in the live demo today, I'm not sure if I can cover everything that I want to cover. I have a repository with the sample code and the walkthrough of the steps. I'm going to show that again in the end, so you can play around with the things that I did today, or that I want to do today later on too. All right, so I hope we're all set. And as a quick introduction to this talk, basically what are the things I'm looking at is, sorry, this one went too quickly. Base situation that a lot of our developers, friends, and we will know is nowadays a situation we have very often of how I'm going to get my code into a executable container image. So there are a couple of options. Coming out of the company Docker and the Dockerfiles that have gone through a certain evolution. There are things like chip, particularly for Java, and this is the JCon, so I'm giving this kind of a bit more attention. Cloud-Native Buildpacks, source to image, there are quite a few. So the why I'm doing this talk here is mostly to show people that there are alternatives to the well-known Dockerfile, that even probably within a Dockerfile, there are options you might not be aware of yet. And maybe try to show you something which make your developer life a little easier, hopefully, let's say. All right, I think the reason why I came to create this talk was one of our developer colleagues reached out to me. They were building some Java applications, said, well, you've been working with containers a bit, so which kind of Java-based container image can you recommend to me? And this is kind of how I want to guide a little bit through this talk to try to get closer to answering this question. Because I said, well, I don't have a straight answer. The answer that we consultants always give is, of course, it depends. What kind of Java application, what Java version, who kind of owns the build process, who owns the container registry, and so on. These are all things we're going to kind of put into consideration, and not just say, well, there's image X and this is most likely the best. So before we go into this, I think this talk is also scheduled as like an entry level. I want to make a quick excursion when I say container image and when I say container, what do I actually mean with that? So to start from a very simple way, if you run your application, might it be a Java application or any other application as a process or an application on your operating system, very often you this process depends on other libraries and dependencies. And one of the big challenges, what we have in migrating to cloud environments is like the dev prod parity kind of issue. Is my development environment very similar to what we do in production, to have like consistent runtimes, have consistent tests and so on, and make things most stable? People came to the idea of bundling the process and application along with its processes, libraries, and dependencies. So from that kind of separation went into a state of an isolation with containers, where there are basically 3 underlying Linux system calls that are the fundamental principles to build a thing that we call container. There are namespaces that define who can see basically the contents of this isolated process and also what the isolated process can see. There is change root, who gives like the container a so-called like root file system to give it the feeling that it's completely in its own world. And the C groups for like controlling what kind of resources is that process and application about to get in terms of like CPU and memory. So with this, we can kind of handle and isolate completely a single process, as it is called, as we call it, container. Now, though executing all those things can be a bit error prone and is not super straightforward. So that's kind of a task that a container daemon will take away from us. A container daemon will normally provide kind of an API to do all those things. The most popular one here is of course Docker, who kind of brought like the container technology to the broader adoption in the world and made it pretty much accessible for everyone. However, we're not limited to Docker here. So most of the things that I'm talking about, some of those things might relate to Docker, but it's not like the standard and the only reference. Now, going back, what is a container image? Now that we have clarified what a container is, so an image is basically a template, or as we are in the Java world, we could, for example, say the container image is like class file, whereas the container is the instantiation or the object. So the template or the container image will bring along all the things that a container needs to run, so that a container daemon can execute an image pretty much everywhere it runs, and it brings along all the things to run and behave in the same way. That's the basic principle. Now, if you want to build an application and put it inside of a container, you should know that those containers are kind of separated into a layered structure. Like those, I should probably say those images are separated into a layered structure. So they don't come as a big blob and must be downloaded fully all the time. So the container daemon will be able to separate those layers and already recognize if a layer is already present. It doesn't need to re-download it or and can leverage what it already has. And if you want to build such an image, you can do that in a layer by layer way. You can say I want a base image from, for example, Ubuntu. Then I want to install a Java runtime. On that Java runtime, I want to copy my application and then wrap all this into a container. Technically, this would always be like a run step that runs the container and the commit step that creates a new image from a running container. Now, again, those steps are fairly cumbersome. However, they work. If you look, however, back in the Docker history, and think Docker came out in March 2013, already in May 2013, there was a reference to a thing called a Dockerfile. So Docker pretty much, you can say, started with using Dockerfiles for making exactly that task easier. So a Dockerfile will basically summarize all those run and commit steps in one go. So we can say we want a base image here. Basically, we read it from top to bottom. Then run an installation process of installing a JDK and all other necessary packages. Then we copy our application in And then later on, we tell the image, so whenever Docker runs that image, it should execute a command, like in this case, java-jar to execute that jar file. And that means wherever I execute that image, it will do exactly the same thing, and it will come along with all the prereqs that it needs. Now, maybe people don't want to do that installation step of the JDK all the time, because it's already kind of a solved problem. And people came up with alternative ideas to say, like, well, I provide my own base image, which is kind of the base layer of the image we are building here. And there are pre-built base images in various combinations. So there's an adopt OpenJDK 11 here. We have, of course, images for various Java versions, from various providers, and so on. So this is like, for example, an OpenJDK, JRE Slim, and so on. And now you can see basically the problem that my colleague was facing when looking at the Docker Hub. There were suddenly so many images. And so where should we start to pick a base container image, which is the best image, which is the what makes the image best? So my question would have been like, how do you use that base container image? And in a standard kind of automated pipeline, you're probably going to go through steps where you code. Then after you code, you build your code. And then if you happen to deploy on a containerized environment like Kubernetes, you need to build a container and then deploy that to that environment. So the scope of the Dockerfile is very often the containerizing step. However, as those pipelines have kind of the nature of doing automated repetitive tasks, we might also consider to extend the scope of the Dockerfile to do more standardized things. For example, including the build step, so that whenever we execute the Dockerfile, that it will always do the same build procedure and packaging procedure, and making that a lot easier to reproduce for everyone, even if they don't use that very pipeline. Now, how should that work? Now, again, we read from the bottom, taking a base image, installing the build tools, copying the source, building the source, potentially removing the build tools again, installing a runtime, and configure everything. So that might lead to a bit of an kind of unstructured Dockerfile. And Docker also realized the need for that you might separate your steps in a Dockerfile into various so-called stages. So you could build Dockerfiles that have a certain logical separation of the things they're going to process. Here I have an example where I have two stages, where in the first one, I'm using a Maven base container image, and I label this as builder. And then I copy the source and I run Maven clean package. So in the end, I'm gonna get a container that contains a jar file which has been freshly built. And then I start another one, another from clause here to say, now I'm going to using some kind of Java base image and copy that part in. So that means that initial container build, this is going to be discarded. The only leftover, what is of use of us, is the freshly built jar file. And we copy that in and assign it to that command. So the advantage here is, whenever we do this, we can make sure that everybody that executes this executes exactly the same build mechanism. So we standardize not only the packaging, but also the build. I mean, normally that should be fairly standard, but people might execute it on different environments, different operating system whatsoever. And the small changes might come up in production when we don't want to have it. So taking this further in terms of standardization might help in your build here. Now, the Dockerfile did not come to an end in its evolution with the multi-stage. In 2018, they started an experimental step with BuildKit, which has now become also a standard in the Docker build mechanism. So this BuildKit promises a lot of things. It's basically those things what we have already seen, what makes a container build process better, like faster builds, smaller images, improved caching, also improved security, and also improvements in the flow logic and parallel and skipped stages. So that kind of, you can say, turned the Dockerfile into a bit of an own programming language, where you really can say, I want to run some steps in parallel, I want to skip some steps if certain conditions are fulfilled, and so on. So here I have an example. This is only in pseudocode, otherwise it would probably not be readable very well, where I, in parallel, built a Java base image where I use my own base OS container. I install a dedicated GRE. In parallel, I run the same Gradle step as before, where I basically build my own Gradle image where I use Ubuntu as a source and then install a JDK in Gradle. And then I have my own designated Gradle and my own designated Java base image. The question will probably soon arise on how far you want to push that and when it still makes sense. This is more just about to show you what you could potentially do, but also that you could potentially lead things into an unnecessary complexity. However, there are some cool things that you can do with that new stuff. So one of the steps that you probably have seen whenever you run a Maven build in a container is that there is no cached objects. So it will always run the Maven command as it would be running it for the first time. Docker containers can mount volumes from the underlying operating systems. However, Dockerfiles are not able to do this and up to this point. So with this feature, you can also mount your local Maven cache. And then if you rerun the container build, you don't have to download all the things again, which might make your execution a lot faster. There are more things to this new build kit stuff. You can, for example, also build to a Kubernetes daemon directly to the local image registry there without pushing your images to a container registry in the first place, and a few more, but that kind of goes out of the scope of what I want to show today. Now, to summarize things, we still don't know what the best Java image is, and I don't think we will ever do. But to summarize what makes a container build good, or what makes an image good. Of course, it's like speed, how fast can you build, how fast can you get your image, then also in size, how small can you get it, how well structured can you have it, and of course, what is the degree of standardization. Of course, we should probably also mention security here. How secure is that image, and how open is it to any kind of vulnerabilities? Now, if we take a step back and say, well, we have learned now that we have, like this, sorry, I'm just gonna resize my Zoom little icon here. Now, going back to this, we have learned that an image consists of individual layers, and they are basically put on top of each other. And by the nature of things, it should of course be that the top layer, the layer where we put our application artifact inside, should be the ones that change more often, as the base operating system layer, which probably shouldn't change that much. And the dependencies in the middle also should not update basically with every build that we do. Having said that, that means that the dependency and operating system layers are mostly cached by the Docker daemon already. So the only noticeable change that you're going to get will most often be in the application layer. Now, if you look more into the Java side of things, in the application layer, what we've done so far is copying a jar file into the new container image. However, even if you look at the jar file also has some kind of nested layers, where you have dependency jars, resource files, and class files. And taking that idea that we just had a step forward, it also should be here that the most frequent changes happen only on the class level and not so much in the dependency jars. Now, one step to approach that, and I hope you can read this well, is using so-called layer jars. So if you run that Java and jar mode layer tools, you can extract those individual layers of a jar file, and then you can nest them step by step into as individual container layers. That will also give you the separation of dependencies, resource files, and actually the application classes. And if those dependencies and resource files do not change, then only the application classes will be added. And hence I would get more speed and efficiency in that step as I would do in optimizing my container image at another point. Now, this was all about Docker. So it would be unfair to skip that as Docker has definitely paved the path to move forward. However, Docker is definitely not the only thing which is around in that ecosystem. So this is kind of a timeline that a colleague from CodeCentric, Jonas Hecht, has sketched in a blog post that I can definitely recommend. So I embedded this here because it shows a little bit about the timeline evolution. When was Docker released? What was prior to Docker, and where are things now? And so you can see, even before Docker was around, there was still about the idea of containers, and there was also the idea of so-called Buildpacks coming from the platform as a service world. So they were initially created by a company called Heroku, and then adopted by Cloud Foundry, who took that PaaS model to like an open source level, which have a different approach of building containers. Then on the other hand, there was an evolution of a Spotify Docker Maven plugin, which made it possible to do a Maven build and not only generate a jar file or building the Java stuff, but also generating a container image out of that build. So you have everything in one step. Now, in 2018, there was also a component called Chip coming out of the hands of Google, like as a very lightweight and fast container build mechanism for Java applications. And then this kind of idea of this build pack surfaced again. So with Kubernetes becoming more popular and the CNCF having like a massive ecosystem, there was the idea to take out the build packs idea out of Cloud Foundry and reuse that as an external component for a standalone mode of building containers. So these are a couple of things that I want to have a look into today and show you. I mean, of course, this has no neither my presentation nor this timeline is complete of the various build options. So there's Podman, there is source to image from Red Hat, and there are a couple of more things. So unfortunately, I can't demo and show them all. But the idea that I just want to give you is there is more out there than a plain Dockerfile, and it would be worthwhile to have a look at all the other options. Now there's Chip to build your, and let's label it, containerize your Java application. And the way this is being done is pretty straightforward. So you have your Java code, and as a requirement, you need to build with Maven and Gradle. And then it's simply a plugin to build your container image. So the interesting thing that you can see in the picture is actually the thing that you cannot see. So this step is being done without the usage of a Docker daemon. So it really doesn't need a local daemon to build the container image. I mean, in the end, the container image is just like a binary structure of files that are residing in the file system. And technically, you don't need a container daemon to build that. And Chip kind of leverages that. So it builds the container image, puts it in the file system, and then you don't need the local daemon to be present. Like, this doesn't have probably a lot of effect on a developer workstation where normally you would have one. But sometimes I've heard situations where people having issues with running Docker daemons as a step in a pipeline build. And this will definitely will be helpful there. As I said, it's not required. I mean, of course, you can build against a Docker daemon and put it in the local registry there, but you don't need to. You can basically directly upload it to a container registry like the Docker Hub. You can export it as a tar file. So you have options. Now, the thing we talked about before, separating the strategy, or like using the strategy to separate class files, resource files, and dependency charts, is also being adopted by chip. So you don't need to do any changes to your build process there. It will automatically create those layers for you within the resulting container image. So you have like a base OS, you have the dependencies chart, resource files, and class files. And whenever you rebuild, only the things necessary will be exchanged. So it's not like copying the resulting jar file of the Maven build into that. All right, so finally, coming to the part of build packs. So the CNCF project is called Cloud-Native Buildpacks, so you can find information on the Buildpacks.io. And if you also take a step back here to say, well, where do those Buildpacks initially come from? And what is, like, why did people create them? So in a time when people did not speak so much about containers, there was also already a platform as a service called Heroku, with the idea in mind to be very developer friendly and basically like provide an API where developers could just like pass their code, and then the platform would detect what kind of code that is, build the code into a runnable artifact, and export it as something executable there. Today we would probably call this runnable a container. At the time, it wasn't called like that. It was basically something which was kind of hidden from the developer anyway, because it was kind of under the curtain of the pass layer. However, this build pack lifecycle is one thing that Cloud Foundry then adopted for a very similar build pack mechanism for the Cloud Foundry platform. So the evolution kind of took a bit of different paths. Cloud Foundry and Heroku went different ways, but with the Cloud-Native Buildpacks idea, things were brought together again. Suddenly, there was much more need to build containers and like Docker or OCI compliant containers outside of a PaaS platform. And the Cloud-Native Buildpacks project kind of defines a definition or a reference architecture, how to build those. And there are quite a few adopters who build their own Cloud-Native Buildpack implementation. There's one, Google does provide an own one. Another one, which is also a project coming out of Cloud Foundry, is the Paketo project. And this is also one we're gonna look into today, as this is like a stable implementation of this. So how would that work? It has a generic CLI, which is called pack, the pack command that you execute in an environment where you normally have your code. From the architecture here, you can see this one will definitely require a container daemon to build. As the way it works, it downloads a so-called builder image. So when you execute pack the first time, it will download a pretty big image, which contains all the build packs and lifecycle detection mechanism. And then within that, so this builder image grabs the code that you have in your local environment. It will run a detection mechanism and say, well, this looks like Go or Ruby or Java or whatever code. So here I have a couple of build packs that I can run it with, and we'll try to build the application image out of that. Of course, you can fine tune and configure things. Technically, you don't need it. The idea of pack is also, of course, to make things as simple as possible for you. And for the most Java applications, especially, I think Spring Boot and Micronaut I've played with, it works really well. So in the end, you're going to get a container image that is being built by the various build packs and includes all the components that you need to run. So technically, this does all the steps that a Dockerfile would do for you, just without writing the Dockerfile. They would bring in all the tested base images, the Java runtime. They would also separate class files from resource files from dependencies and optimize the image as good as it can. Now, another important thing here is a so-called rebase functionality. So in the beginning of the talk, I kind of told you that most often the application layers change and that the underlying layers will change in a very less frequent kind of iteration. Now, however, they might change. I mean, it is not too uncommon that a certain base image of a Linux operating system suddenly says, well, we have some security vulnerabilities in this or that image, and you need to run a patch. So in this case, a rebuild would do a bit of unnecessary things because the application layer and the dependency layer do not need to change. It's only the base image that needs to change to patch some of the vulnerabilities down. So in this case, you can exchange the base OS layer dynamically. Now, why would this make sense? I mean, if you, well, this might become clearer once you see the Paketo implementation. Now, of course, we are focused on Java here. However, not all of the microservices that are in your environment might be a Java implementation. And so Paketo builds build packs for multiple runtime and language support. And now if you imagine you have like a polyglot environment of microservices, say some Ruby, some Go, some Java, some PHP whatsoever. And now there's a situation that something like Heartbleed or a shell shock or whatever vulnerability becomes popular, and you know, some of your systems might be affected. So the first thing you probably try to do is say which of the images are being affected. Now, if you use things like Dockerfiles and you have different environments, you would probably have to go to each and every Dockerfile and say, is this an affected base image, and do I have to patch that? Now, if you use things like Cloud-Native Buildpacks, that means that your base layer of all of your images are identical. They may be different on a higher level in the build pack layers, where you say, of course, you don't need a Java runtime in a Go container and vice versa. But you can, of course, quickly identify, am I affected or am I not affected? Or do I have to exchange now all of the build pack images, or do I have to exchange none at all? This was also a concept in Cloud Foundry, because like Cloud Foundry internally also was using containers, and they had exactly one base image for all of the applications. And that made it very easy for maintenance. So it was just like updated for everyone in kind of the same procedure, with no evaluation. Where do I need to change something in the Dockerfile, and do I need to retest it, and so on. So this is kind of when this value becomes effective. All right. So now going more into Paketo, especially on the Java side of things, running the pack command will create you a Java image. As I said before, it also will differentiate into class, resource, and dependency jar files. If you happen to use Spring Boot, there is also an even easier integration in there, or like, let's say, an alternative step where if you don't want to run the pack command to build and package your image, you can also use Maven and Gradle directly to execute a Maven build and then have that result in a resulting container image also using Paketo technology. So the difference will be that the actual compilation and the JDK that you're going to use is going to be the one from your local environment, and then the JRE and all the other mechanisms will be in the run image, as opposed to using the pack. Then the JDK and later on the JRE will be provided by the build packs. So this is an option for you then. Now, coming back to the question, like, what is the best container image? This is kind of, or the best Java-based container image. This is kind of hard to say because there are many different options there. So one thing that I would counter ask is like, who owns the image? I mean, if there is something happening in your container during productive runtime, and especially if something happens in a layer that you didn't build yourself, who is going to be called then? And who is going to be responsible? So if you happen to run in an environment where people maintain an own registry of pre-built images and scanned images and validated images, then I would say that's you're fine. Go ahead and use that one. As soon as you get into the role that you need to test and validate your own images and are responsible for that, then some things like Cloud-Native Buildpacks might make sense for you. Also, of course, who owns the build process? I mean, how much effort do you as a developer need to put into write and validate the Dockerfiles and validate the base images? Also here, something like chip and or Paketo might make sense for you. Of course, this will not always work. I mean, you will, the higher abstractions always means you need to narrow down some things. I definitely had some situations where it was just not applicable. And that means you can always fall back to using a Dockerfile. That one will always work. The question is more like, do you always need to go that route? All right. So we're gonna come, how much time do we have left? About 7 minutes. That's not super much. Again, well, this is not so important right now. I have built this this code repo here, which I have shared in my slides here. I have also put this or opened this here in my Visual Studio Code. There is like a walkthrough kind of section here where I do various steps, like building a container with a plain Dockerfile, then using predefined images, and looking at the history, using the dive tool to access the images. I will probably be only able to show a few. So in a very simple form of building a Dockerfile, I'm going to do that. I hope you can see this well. If you've used Docker earlier on, you will notice that the outline and the output of will be different to what you've seen before. So you most likely have seen Dockerfiles output looking like this, where you send your build your context to the daemon, and then the individual steps will do. So this is what the newer looks like. I think even with the newer Docker versions, it's like set by default. And yeah, so what you're gonna get here, you construct those things into those layers. If you do a Docker history of that container, you will see exactly the things that I've shown before. Somebody had built that original image. That's probably some Linux distribution, then installing a Java runtime. And then this copy step is basically the part where we put in our jar file. Now, one of the new things that I wanted to show you is not only using that multi-stage Dockerfile. No, I don't want to install it now, just get away. No, that's that multi-stage where I use a Maven container as a build container and this adopt OpenJDK as a run container, where I do this copy step from.
Entschuldigung, ganz kurz die Unterbrechung.
Ja.
Da wäre eine Frage im Chat, ob man den Link mit dem Chat oder per Twitter posten könnte.
ob man was per To-Do posten könnte?
Den Link. Ich habe jetzt leider nicht mitbekommen, um was es genau ging.
Den GitHub-Link.
Ich vermute mal ganz stark.
Ja, also das machen wir einfach gleich. Ich kann ihn natürlich.
Dankeschön.
Yeah, kein Problem. Okay, so before I get used too much to writing things, saying things in German, I'm going to do it in English again. So this is that. So here you have various Docker files you can play around with. And you see, this is that experimental Docker file. And the difference that you have here is that mount type where you cache something. So what I'm going to do now is I'm going to do, there's too many windows open. I'm going to run that experimental cache file. And now you will probably see, I think I've built it before, so it remembers that it's using all the cache layers, so it goes really quick. So that's, of course, like cheating. Now, if I go into my code, and I'm just going to rename that method. Nothing big, but definitely will trigger a rebuild of the code. And if I do that now, you will see when it comes to the Maven step, like here, it won't start to download all of the Maven things again. So it's just like rebuilding as if you would run Maven locally. So this is definitely a lot faster than doing the entire build. And so especially in terms of local development, this might save you quite a bit of time. Okay, so I hope you were able to see that, as opposed if I don't do it that way, and I'm using the standard multi-stage build as it used to be, I can quickly kick this off. And if it runs the Maven build now, it will have to download all the libraries over and over again because it doesn't know there is a cache. So that's the point that you might want to do in a pipeline for having it like very consistent. For local development, it might not make sense all the time. So while this is running, and you see that it has taken a longer time than the other one. We're now in the testing phase. So in this demo, it's not very much different. I've run the experimental one in a lot faster than 28 seconds, but I think you get the point of what I try to say here. No, too many things popping up here. So I have more things in the chat. Okay, I've got 10 minutes left. That's good to know. I think I will be fine. Going back to that walkthrough here. What else did I want to show? Yeah, so even with that experimental feature, so if I go on Docker images now, and these are the 3 images that I had just built. If I do like a Docker history now, and I use the latest one, that's the one right here, 255. It is still, you see this by the 3 layers that we added with the build kit, but it's still the case that we just simply copy the jar file over. So we didn't optimize here in that aspect. If we want to do this, we need to use that layer jar. So this might also take a second. I'm going to try that. So, okay, this was fairly quick because it had something cached already. So if I look at that image, and this is like the layer 1 here. So I do a Docker history on F1. We can see now that there is a separation here. So we see that the dependency layers of our jar file makes about 18.9 out of 19. And the rest is merely in the range of kilobytes. And these are normally the parts which actually change. I mean, you probably would do a bigger change than I did with just entering some characters. But still, it would only affect that layer to be changed once you start to rebuild. Now, what did I else want to show? Looking at things like chip. I'm trying this one too. So as said before, well, I have my Docker daemon now turned on. So you probably don't believe me that I say I don't need a Docker daemon, but stopping and starting that might kill my remaining time of the demo. So I just need you to believe me. In the end, you could see this build step was really, really fast. It only took about 10 seconds. And if I look into the images, we will not find the chip image on the very top. We will find the chip image on the very bottom. And it says it has been created 51 years ago. That is, of course, a lie, but this is a problem with Docker, that Docker creates a new image ID on every build and takes the build date into consideration. So even if you do a totally identical build at two different points in time, you're going to get different build IDs, which doesn't make a lot of sense. That's why Chip and Paketo just specify a dedicated point in time very, very far ago. And this will always apply to the build step to keep this consistent. You could change this, but then you would sacrifice the option to have like a fully reproducible build ID. However, what I really want to show is if we look into that, we see here what the chip piece has actually created. And we also see here the dependency resources and class files. Again, the class files are very, very, very small here. So this one is optimized in that aspect as well. So finally, what we're going to need is pack. The command will be pack build and then specify your image name. So I'm not going to tell pack this is Java or where is the POM file or whatever. I'm just executing that. And out of my local environment, it will probably find the pack file. So first it's going to check where I need a builder image. That is something that I've already downloaded. Then it will detect I have a JVM 11 or Java version 11. So now it's going to complete the build. This also has a caching mechanism, so it just rebuilds in a few seconds. And once it has completed that, it's going to download the JDK and build the remaining image. So additionally, you can also see, where's that? I'm lost in my own build here. So I think that the room will close here in a second. I'm sorry, well, I got to interrupt at this point. Do you have any final questions about that? Otherwise, please feel free to ping me on Twitter. I think you have also recordings of that talk from a user group with more demo time. I'm running here into a hard stop, I think. Check the watch. It's 49. I think we're gonna come to an end. So all I want to say is thank you for listening. I hope you learned something new, or I could show you something that you didn't know yet. Feel free to ping me if you want to know more. Here are my details again. And with that, I just wanted to say thank you for listening.